You hold a phone thinner than a notebook. Tap the screen. Open a video. Send a message. Turn on the map. Then slip it into your pocket as if it were nothing more than a harmless, everyday object. And yet, beneath that layer of glass and aluminum sits a system holding energy in a state as tense as a drawn string. Modern convenience is built on a very blunt paradox. If we want devices to be thinner, stronger, and longer lasting, we have to pack more energy into the same volume. In other words, we are compressing an energy bomb into an object that fits in the palm of your hand, then giving it the very reassuring name of a battery. A full battery sounds comforting. But in physical terms, that is actually when the system is being pushed furthest away from equilibrium. A lithium-ion battery does not store electricity the way a bucket stores water. It works by forcing lithium ions to move back and forth between two electrodes, while electrons are compelled to take the longer route through an external circuit to do useful work for you. What we call 100% battery is really the moment when the materials inside are carrying greater chemical stress than usual. Your phone is not a quiet lump of stored energy. It is a ceasefire maintained millisecond by millisecond. To understand why such a tiny battery is so sensitive, look at what we demand from it. Users want a thinner phone, yet they also want to record high-resolution video for hours. They want fast charging that finishes in the time it takes to drink a cup of coffee. Yet they also expect the battery to remain healthy for years. They want a lightweight device, but they also want enough performance to edit photos, play games, and cut video. All of those demands are forced into the same place. Higher energy density, which means cramming more work into a smaller space. The problem is that once energy is compressed that tightly, the system's margin for error shrinks with it. A good battery is not good because it is powerful in the muscular sense. It is good because it can preserve an extremely fragile chemical structure, without allowing that structure to destroy itself. Inside the battery are thin layers of material stacked closely together, separated by a membrane far thinner than most people imagine. That separator does not create electricity. It performs one brutally important task: keeping the positive and negative sides from making direct contact. If that boundary is breached, the battery stops being an energy storage device. It becomes an extremely expensive shortcut to a short circuit. That is why a battery does not need a dramatic impact to get into trouble. A small dent, one drop against the edge of a table, or repeated pressure inside a tight pocket can all damage microscopic structures that the naked eye cannot see. The danger is that batteries rarely send warnings in the style of an action movie. They swell slowly, heat up quietly, and only once everything crosses a threshold do people remember that the thing they charge every night was never truly gentle to begin with. When a battery is working normally, lithium ions move through the electrolyte like passengers staying in the correct lane, while electrons are routed through circuitry to light the screen, power the processor, and vibrate the phone in your hand. The entire system depends on those flows staying on course. Once part of the material begins to degrade, that order starts to crack. One of the biggest problems is heat. Heat is not merely a consequence of failure. It is also an accelerant. When a battery gets too hot, side reactions begin to appear more often. The electrolyte can break down. Gas can form. Pressure inside the cell can rise. And the electrode materials can be damaged. That is why a failing battery is often hot, swollen, and losing performance at the same time. It is losing its ability to keep its internal reactions under control. If the situation keeps worsening, the battery can enter what is called thermal runaway, meaning a loss of thermal control. The name sounds technical, but the image is very ordinary. The system heats up, and that very heat causes it to generate even more heat. like brakes that have already burned out and only become more useless the harder you press. From that point on, the chain reaction can unfold with terrifying speed. Not because the battery has gone crazy, but because physics is no longer giving it a safe escape route. In the world of high-energy materials, stability is not the default state. Stability is something that must be guarded continuously. That is when the Battery Management System, or BMS, takes center stage. Users often think they are controlling the phone. A more accurate version is that you are making requests, while a tiny chip is deciding whether those requests are safe enough to be allowed. It measures cell voltage, tracks charging and discharge current, monitors temperature, cuts off charging when limits are exceeded, and reduces performance when it detects risk. When your phone suddenly dims the screen, slows down, or refuses to fast charge when it is too hot, that is not the device acting weird. That is the BMS doing the least glamorous but most important job in the entire machine. The taming of modern energy has never been about making electrons weaker. No one wins by persuading electric current to behave through sentiment. The only workable method is to build an extremely strict internal legal system, where every millivolt is monitored like cargo passing through customs. That is why the modern smartphone is really an alliance between chemistry, materials science, and semiconductor LAW. It runs so smoothly that we forget a negotiation is taking place every second between performance and safety. Higher current generates more heat. And as you've already seen, heat is not a passive byproduct. It accelerates unwanted chemical reactions, degrades materials faster, and increases internal resistance over time. That's why batteries that are frequently fast-charged tend to age more quickly. They lose capacity. They struggle to hold charge. They become less stable. It's not because fast charging is bad in a moral sense. It's because it asks the battery to operate closer to its physical limits more often. And yet, despite all of this, fast charging exists and works remarkably well. That's where modern engineering steps in again. Battery management systems don't just monitor temperature and voltage, they actively shape the charging process. Fast charging is rarely a constant, aggressive push from 0 to 100%. Instead, it usually happens in phases. At lower charge levels, the system allows higher current because the battery can accept it more safely. As the charge increases, the system gradually reduces the current, easing the battery into a more stable state. It's less like flooring the accelerator, and more like a carefully controlled sprint that slows down before the finish line. Manufacturers also design electrodes, electrolytes, and separators specifically to handle these stresses. Better, materials are engineered to allow faster ion movement, improved heat tolerance, and greater structural resilience. In a way, fast charging is not just a feature. It is the result of countless small compromises, optimizations, and protective mechanisms working together, so that the user experiences something simple, while the system handles something incredibly complex. And that brings us back to the quiet paradox at the heart of your phone. Every time you plug it in for a quick boost before heading out, you are asking a tightly balanced chemical system to move faster than it naturally wants to. Most of the time, it agrees. Not because it's easy, but because an entire invisible infrastructure has been built to make that agreement possible. So when your phone slows down, charging near the top, or warms slightly during a rapid charge, those are not signs of inefficiency. They are signs of negotiation. A system carefully deciding how far it can be pushed, without crossing the line where convenience turns into instability. And that line, as it turns out, is thinner than the glass you swipe every day.